Now we're going to use elementary kinetic theory to estimate the coefficient of viscosity, and once again this is not a very rigorous approach that we will take here. So if you remember, Pzx is the tangential stress, which is basically the force in the x direction above the z is equal to constant plane per area of the z is equal to constant plane. So this is basically 1 over the area multiplied by, using Newton's second law, the change in momentum dpx dt, x component of the momentum, derivative with respect to time. So linear momentum is mv, so derivative with respect to time is ma, so F equals ma, Newton's second law. And let's write what this really means explicitly. This is the mean increase per unit time and per unit area of the plane. So this plane is z is equal to constant plane of the x component of momentum of the gas above the plane due to the net transport of momentum by molecules crossing the plane. So if you concentrate on z is equal to constant plane, so this is our z is equal to constant plane here. And above this plane we have the gas that we're concentrating on, and there is a net transport of momentum from molecules crossing this plane. So there are molecules going below the plane, there are molecules going above the plane, and there's a net transport of momentum by these molecules, and that is, if you look at the net transport of momentum per area per unit time, that gives us the tangential stress, the force per area of the plane. Now I would like to estimate how many molecules are basically transporting this momentum. So we need to talk about the flux of molecules, the number of molecules crossing the z is equal to a constant plane per area per time. That is basically the flux of molecules. This is molecular flux. This we can estimate basically by saying that all dimensions x, y, and z are equally probable, so we can have 1/3 of the molecules on average moving along x, 1/3 moving along y, 1/3 moving along z, and in the positive z direction or negative z direction, we would have half of them, half of the molecules that have a z component of their velocities moving. So we would have 1/6 of those molecules. So we can say that this is, it can be approximated as 1/6 number of molecules per unit volume multiplied by the mean speed per molecule. So number per volume times dx dt or dz dt in this case, you would have number per area per unit time. So that's the molecular flux. Once again, this is the approximation we used at the beginning of our discussion in chapter 1, and also this came up again when we talked about the molecular beam apparatus. But if you remember, if we go back to basically our discussion of the molecular flux in Maxwell velocity distribution molecular beam apparatus, it was actually 1/4 nv bar because of this spherical distribution of molecules. But this is also a good approximation. We can use 1/6 nv bar using this this argument of random direction. So each such molecule that is basically moving in positive z or negative z direction will have a speed. So each such molecule has a speed that is the x component, which is z minus the mean free path L, which is after the previous collision a distance L from the plane. So I look at a molecule that is moving in the positive z direction, so the number of these molecules per area per time is 1/6 nv bar, and then there is a number of them that are crossing the below the plane, that is 1/6 nv bar also. And if I look at a distance L from the mean free path from the plane, basically there was the last collision that changed the direction of the velocity, and therefore they picked up a speed, a velocity x component at z minus L, and it's the same thing that is going to be the speed when they are crossing the plane, because we on average we don't have a collision in between z minus L and z. So the same thing is true for the molecules approaching the plane from above. If you look at a distance L from the plane, and you can see that there was the last collision at at z plus L, so they picked up a speed at z plus L. The velocity x component at z plus L is the same because on average there is no collision between z plus L and z. So these molecules are approaching this plane with the speed that they obtained at z minus L and z plus L. So what I'm interested in is the net momentum transported across the plane. So let's talk about this momentum that we're transporting. So basically I'm trying to get the mean x component of momentum which is transported per unit time per unit area across the plane in the upward direction. I'm also interested in what's happening in the downward direction. So what is this momentum that we're transporting across the plane in the upward and downward directions? Well, you can see that the number of molecules that are transporting this momentum is 1/6 nv bar, and they have a mass. Each molecule has a mass m, and then they have a speed that they picked up at a distance L from the plane. So it is either z minus or z plus L. So this basically will depend on so this didn't fit here, so let's rewrite it here. This is basically 1/6 nv bar, the number of molecules crossing the plane per unit area per unit time. They each have a momentum mass times their speed ux, which is z plus or minus L, depending on if they're moving upward or downward. If it is upward, it is minus. If it is downward, it is plus. So they picked up at z plus L, and they're carrying this momentum to the plane. Okay, then I would like to calculate the net momentum transported. So if I calculate the tangential stress Pzx, this is going to be equal to 1/6 nv bar m, the momentum that is being transported from below the plane. They have a speed ux z minus L, and then the ones that are crossing the plane downward, ux at z plus L. So here L is the mean free path, which is a small number, is very small. So basically I can use Taylor's expansion. So if I use Taylor's expansion for ux of z plus or minus L minus or plus, this is going to be around L is 0. So this is going to be, for the first term, L is equal to 0, so you would have ux of z, and the second term you would have minus or plus del ux del z evaluated at L is equal to 0 times L minus 0. So this is basically Taylor series, Taylor's expansion for small l. So you can see that This is going to give us, for the tangential stress, 1 over 6 nv bar, the momentum that comes from the top, from the bottom, the molecules crossing the plane, approaching the plane from below the plane, they have ux of z minus del ux del z, and then minus ux of z minus del ux del z, and these two will disappear, and we will have basically as the answer the tangential stress is 1 over 6 n v bar m minus 2 it's not the derivative that is going to disappear, so I have made a mistake. It is the ux of z that disappears. So we have, for the tangential stress, Pzx is 1 over 6 nv bar m minus 2 del ux del z. So this is going to give us, as the final answer, minus 1 over 3 n v bar. So remember that we have the mean free path here as well, L. So this is going to be 1 over 3 n v bar m L del ux del z. So this number in the parentheses is basically our coefficient of viscosity minus del ux del z. So we have found that the viscosity can be estimated as 1 over 3 the number of molecules per volume, the mean speed per molecule, mass of one molecule multiplied by the mean free path. And we have also found out that indeed this tangential stress Pzx is proportional to minus the gradient of the tangential speed with respect to the z axis, with respect to the depth of the fluid. Alright, so we're trying to calculate or estimate the coefficient of viscosity for a dilute gas. First of all, this tangential stress was related to the coefficient of viscosity and the gradient of the tangential speed. So if you remember, this we have found out, Pzx is minus eta del ux del z, and eta was measured in units of poise also, which was kilograms per meter second. Now this tangential stress is the force per area, tangential force per area, which is above the z is equal to constant plane x component. So that's 1 over area, the change in linear momentum x component with time. So it's the mean increase per unit time and per unit area of the plane. So it's the area of the plane, z is equal to constant plane, of the x component of momentum of the gas above the plane due to the net transport of momentum by molecules crossing the plane. When we say molecules crossing the plane, there are molecules going above the plane and molecules going below the plane. So on average, we can estimate the molecular flux, the number per area per time, to be 1 over 6 nv bar, because we have three axes, three independent degrees of freedom x, y, and z, and we have equal likelihood for plus z direction and minus z direction. That gives us a factor of 1 over 6. Without considering the spherical distribution of molecules. If you consider the spherical distribution, you would find out that it is 1 over 4 nV bar instead of 1 over 6 nV bar. And each such molecule will have picked up a speed at a distance of a mean free path below the plane or above the plane. So because it's the collisions that changes the x component of the velocity here, and on average there will be no collisions within a distance of a mean free path. So we have picked up a distance at z plus L for molecules going below the plane, and we have picked up a distance ux at the position z minus L for the tangential speed for molecules that are crossing above the plane. So the mean x component of momentum transported per unit area per unit time across the plane is in the upward and downward directions, and for the upward direction it's the molecules that have picked up a tangential speed at z minus L, and for the ones that are crossing from above the plane to below the plane, they have picked up a speed at z plus L. So the net momentum transported is the difference between these two. There are 1 over 6 nV bar molecules per area per time crossing the plane. They each have a momentum m ux z minus L if it's coming from below the plane, and ux z plus L if it's coming from molecules above the plane and crossing the plane in the downward direction. L is the mean free path, which is a very small number, so we can use Taylor's expansion. So the tangential speed ux of z plus L or z minus L is ux of z plus or minus del ux del z evaluated at L equals 0 multiplied by L or L minus 0, which is the Taylor's expansion in the first two terms. So we're basically using this approximation for small l. And we have for the tangential stress 1 over 6 nV bar m. For ux of z minus L, we substitute ux of z minus del ux del z multiplied by L minus ux of z plus L is ux of z plus del ux del z times L. So with the minus sign they become minus ux of z minus del ux del z times L. Ux of z is cancelled, and we find that the tangential stress is minus 1/3 nV bar ml del ux del z. So the coefficient of viscosity is approximately 1/3 nV bar ml. N is number of molecules per volume. V bar is the mean speed per molecule, m is mass of one molecule, L is the mean free path, and we indeed see that the tangential stress is proportional to minus the gradient of the tangential speed with respect to the